For years, space has been framed as the place humanity is supposed to go next, but that idea becomes much less convincing the moment you start looking at the reality behind it. Because this is not just about reaching space, it is about surviving it. And those are two very different things. The deeper you go into that difference, the more unsettling the conclusion becomes. And if you enjoy watching these type of videos, then subscribe to the channel. Let's begin. Space does not start killing you because it is far away. It starts killing you because your body cannot function in it without constant mechanical support. That is the first thing most people get wrong. You hear the word vacuum and it sounds like empty space, like nothing is there. But that word hides the real problem. Space is not just empty. It is a place with almost no pressure, no breathable air, intense radiation, and extreme temperature differences. On Earth, your body lives under about 101.3 kilopascals of pressure, or 14.7 pounds per square inch. In open space, that external pressure drops towards zero. That is not a small difference. That is a direct threat to basic human survival. Your body is built for Earth so completely that most of the support systems are invisible to you. You do not think about pressure holding your fluids stable, or the air helping your body manage heat, or oxygen moving into your blood under normal atmospheric conditions. But all of that matters. The human body is a wet chemical system, and it only works inside a narrow range of conditions. Remove those conditions, and things start going wrong very fast. This is why the idea that a person could just go into space and somehow endure it for a short time is false. Human physiology is not flexible in that way. The first serious problem is pressure loss. When pressure drops sharply, the boiling point of liquids also drops. That means exposed moisture can begin to vaporize at much lower temperatures. You do not explode in space, that part is exaggerated, but you do swell. Gases in the body expand and the body starts losing normal control almost immediately. Blood inside intact vessels does not suddenly boil everywhere, but tissues do not behave normally, and the damage begins fast. The most important number here is not dramatic, but it is devastating. You may have only around 10 to 15 seconds of useful consciousness after sudden vacuum exposure. That means no heroic reaction, no long struggle, no time to think clearly. You black out very quickly because your brain stops getting the oxygen conditions it needs. And that leads to another common mistake. People think they could just hold their breath for a moment and survive. That is exactly the wrong response. Holding your breath during rapid decompression can make things worse because pressure differences can damage the lungs. The right instinct on Earth becomes dangerous in space. That tells you how unnatural the environment is. Even your most basic reflexes are not reliable there. Then there is temperature, and this is another place where people picture the wrong thing. The usual version is that you would freeze instantly. That is not the first thing that would happen. Space has no air. So heat is not removed from your body the way it is on Earth. Space is actually poor at carrying heat away through direct contact because there is no atmosphere around you. The problem is not simply that space is cold. The problem is that your normal thermal environment disappears, and now heat management has to be engineered artificially. Also, space is not one stable temperature. That idea is too simple to be true. In direct sunlight, surfaces in orbit can reach more than 120 degrees Celsius, about 248 degrees Fahrenheit. In shadow, they can drop below minus 100 degrees Celsius, below minus 148 degrees Fahrenheit. So the danger is not one steady condition. It is violent thermal contrast. One part of a spacecraft can be heating intensely while another part is losing heat fast. For humans, that means survival depends on active temperature control, not on just wearing something thick. This is why a spacesuit is not really clothing. It is better understood as a small personal spacecraft. It has to provide pressure, oxygen, carbon dioxide removal, cooling, humidity control, communication, and some protection from tiny high-speed impacts. A person in a spacesuit is not dressed for the environment. A person in a spacesuit is being kept alive by a machine that is replacing part of Earth. The suit is not convenience, It is the minimum system required to stop the environment from killing you. And even that system comes with limits that show how harsh space really is. Modern spacewalk suits usually operate at pressures well below normal sea level atmosphere. Because of that, astronauts often have to spend long periods breathing pure oxygen before going outside. The reason is to lower nitrogen in the body and reduce the risk of decompression sickness. Think about what that means in direct terms. Even after launch, even after a safe trip into orbit, even after reaching a controlled spacecraft environment, a human still cannot just open the hatch and step outside. The body needs preparation because the outside environment is still physiologically extreme. That brings us to the bigger point. In deep space, survival is machine-dependent every second. On Earth, if a building loses power, the situation may be serious but usually not immediately fatal. In space, if life support fails, the environment becomes deadly almost at once. Oxygen has to be supplied continuously, carbon dioxide has to be removed continuously, pressure has to be maintained, temperature has to be controlled, water has to be managed, waste has to be processed. Every one of those systems is part of staying alive. If one critical part fails and backup systems do not respond, the margin between normal operation and disaster can be extremely small. That is why space travel is not transportation in the way people usually think about transportation. A car moves you through a world your body can already survive in. A spacecraft does something much harder. It carries a tiny artificial environment around you because the real environment outside is incompatible with human life. You're not traveling through space as a naturally adapted organism. You're being carried inside a fragile, moving life support shell that has to reproduce essential parts of Earth the whole time. And before anyone starts talking about Mars, deep space missions, colonies, or travel to other stars, this is the first barrier that has to be faced honestly. Human life is not space compatible by default. The body does not negotiate with vacuum. It does not improvise around zero pressure. It does not casually handle radiation, thermal extremes, or total dependence on machines. Every second a human survives in space is a second won by engineering, not biology. So the basic conclusion is simple, and it is more severe than most people realize. The first challenge of space travel is not distance, speed, or engines. The first challenge is that human beings are not built to exist in space at all. You do not move through space the way animals move through Earth's environments. You move inside a manufactured bubble that must actively keep your body in an Earth-like state at every moment. The mission is not just getting somewhere. The mission is preventing physics from shutting the human body down before you arrive. And once that is clear, the next problem becomes even harder. Because even if you build that protective bubble perfectly, the human body still starts changing the moment the gravity is no longer normal. That means the environment does not stop attacking you when you seal the hatch. It keeps attacking you from the inside. Gravity is not just something that keeps you on the ground. It is one of the main conditions your body was built around, and the moment that condition changes, your body starts changing with it. That is the next hard truth about human space travel. Even if you solve vacuum, pressure, oxygen, and temperature, even if the spacecraft keeps you alive perfectly, the human body still does not remain normal once gravity is removed. It starts adapting to a new environment, and that adaptation is bad for long-term health. Every part of you has been trained by 1G your entire life, about 9.81 meters per second squared. Your bones are constantly loaded by it. Your muscles constantly push against it. Your heart and blood vessels constantly work with it. Your balance system reads motion through it. You do not feel this as effort because it has always been there. But that constant downward force is part of the reason your body stays the way it is. Take it away, and the body does not stay strong out of loyalty. It starts conserving effort. It starts remodeling itself for a world where support is no longer needed in the same way. So the question is simple. What happens to a skeleton when it no longer has to carry weight? The answer is bad, and we already have real data on it. In microgravity, astronauts can lose around 1% to 2% of bone mineral density per month in weight-bearing parts of the body if countermeasures are not enough. That is an extreme rate compared to bone loss during normal aging on Earth. This is not a small decline. This is not just becoming a little weaker. This is the body actively dismantling part of its own structure because the usual mechanical demand is gone. The hips, the spine, the legs, these are the regions that normally work against gravity all day on Earth. In orbit, that load disappears. The body reads that as unnecessary expense. Bone tissue is constantly being broken down and rebuilt even on Earth. But in microgravity, that balance shifts in the wrong direction. More bone is lost than replaced. Over time, that means weaker bones, greater fracture risk, and another problem people do not think about enough. The calcium released from that lost bone enters the body's fluid systems and can increase the risk of kidney stones. So deep space travel does not just make you weaker, it can turn your own skeleton into a medical problem, and bone is only one half of it. If your body stops needing to support itself, what do you think happens to muscle? The same logic applies. Muscles do not stay large and strong because they are morally committed to you. They stay strong because they are used. In microgravity, the legs, lower back, and postural muscles no longer carry body weight the way they do on Earth. That means they start shrinking, strength falls, endurance falls, coordination changes. Astronauts on the International Space Station exercise intensely, often for hours a day, specifically to fight this problem. And even then, they still come back physically deconditioned compared with where they started. That matters because it changes what arrival means. People talk about reaching another planet as if getting there is the main victory. But what if after months or years in reduced gravity or weightlessness, your body is too weak to function properly when you arrive? What if you can technically reach the destination, but standing, walking, lifting, or reacting to emergencies becomes harder because the trip itself has already stripped away your physical margin? Then travel is not just transport. It becomes a process that damages the organism before the mission is even halfway complete. Then there is blood, and this problem starts almost immediately. On Earth, gravity pulls bodily fluids downward. In space, that distribution changes. Fluids shift upward toward the chest and head. That is why astronauts often get puffy faces and thinner-looking legs in orbit. But the appearance is not the real problem. The deeper issue is that your cardiovascular system starts adapting to a world where it no longer has to push blood upward against gravity in the same way. Plasma volume can decrease. The heart and circulation change their operating pattern. Over time, the body starts becoming less prepared for normal upright life on a planet. That is why some astronauts returning to Earth can have trouble with standing tolerance. This is called orthostatic intolerance. In direct terms, your body becomes worse at handling the simple act of being vertical under gravity again. So even if space does not kill you during the mission, it can still train your body away from the conditions needed for normal human function. That should make the whole idea much more serious. You're not just taking a trip and coming back tired. Your body is being reconditioned for an environment that does not support long-term human health. Now, the next part is even more unsettling because the effects are not limited to bones, muscles, and blood. They can also reach the eyes and possibly the brain. Some astronauts on long-duration missions have experienced problems grouped under spaceflight-associated neuroocular syndrome. That includes structural changes in the eye and vision changes. One leading idea is that fluid shifts toward the head may contribute to altered pressure around the optic nerve and changes in the shape of the eyeball. The important point is not that every detail is solved. The important point is that this is real enough to worry space agencies, and the implication is severe. Leaving Earth can change how your eyes function at a structural level. That matters because vision is not optional in a spacecraft or on another world. You need it for navigation, maintenance, docking, repair, emergency response, science work, and basic survival. If long missions can alter vision and eye structure, then the body is being affected in places that are mission critical in a very direct way. And the disturbing part is that this is happening not because of an accident, not because of a failure, but because the environment itself is different from the one humans evolved under. So naturally people jump to the backup idea, artificial gravity. Spin the ship, create a gravity-like force, solve the problem. But this is where the engineering turns ugly very fast. Artificial gravity through rotation is not fake in the sense of being useless. It can create a force that pushes you toward the outer edge of a rotating system, but making it comfortable and practical is difficult. If the structure is too small, the rotation has to be faster to create enough force, and fast rotation can produce strong Coriolis effects that make people feel disoriented or nauseous. Move your head, move your arms, even simple motions can start feeling wrong. A small spinning spacecraft sounds efficient, but it can become physiologically unpleasant. A larger rotating habitat is better, because the motion feels more natural and the gravity difference across the body is reduced. But now the structure becomes huge. And once the structure becomes huge, mass becomes a major problem, and mass leads directly into propulsion, construction, launch costs, mechanical stress, and failure risk. So artificial gravity is not a clean solution waiting on the shelf. It may help, but it pushes the spacecraft toward much larger and more complex designs. That is the real point of this section. The body is not just inconvenienced by microgravity, it is altered by it. Bone declines, muscle shrinks, blood shifts, circulation adapts, vision can change, and the longer the mission lasts, the more these effects matter. So even after you build a sealed vehicle that protects humans from vacuum, the environment still keeps attacking from another direction. It attacks by removing the one constant physical condition your biology has depended on since birth. And that should raise the tension even more, because gravity loss is still not the worst long-duration threat. Even a perfectly pressurized spacecraft with excellent exercise systems cannot remove the next problem. Outside Earth's protective shield, deep space is filled with radiation that does not just weaken you over time, it can damage cells, raise cancer risk, threaten the nervous system, and turn long missions into a biological countdown. Deep space is not just empty distance, it is an environment that actively damages living tissue, and Earth is protecting you from most of it right now. That is what makes radiation one of the most serious barriers in human space travel. On the ground, you're not exposed directly to the full radiation environment of space, because Earth gives you two major layers of protection, the atmosphere above you and the magnetic field around the planet. Those two systems absorb, scatter, and deflect a huge amount of harmful radiation. Without them, the biological situation changes immediately. That is why low Earth orbit and deep space are not the same challenge. Staying close to Earth is still dangerous, but you are operating partly inside Earth's protective influence. Go farther out, and that protection drops away. The farther you move from Earth, the more directly the crew is exposed to radiation that human biology did not evolve to handle. That is not a side problem, it changes mission design from the start. So what exactly is out there? At minimum, there are three major radiation threats that matter. The first is galactic cosmic rays. These are high-energy particles coming from outside the solar system. The second is solar particle events, when the sun releases bursts of energetic particles, especially protons, that can sharply increase radiation exposure over a short period. The third is trapped radiation around planets, such as Earth's Van Allen belts, where charged particles are held in place by magnetic fields. These are not three versions of the same thing. They behave differently, arrive differently, and create different shielding problems. That matters because a spacecraft does not get to prepare for one clean, predictable threat. It has to deal with multiple radiation environments at once. One source may be a chronic background problem, another may be an acute burst, another may be tied to a specific region of space. None of them care whether the crew is in transit, asleep, busy with repairs, or already weakened by months in flight. Radiation is not an occasional inconvenience, it is part of the environment. The obvious answer sounds simple: add shielding. But this is where the problem turns brutal. Shielding means material, and material means mass. If you want meaningful protection, you usually need substantial amounts of matter between the crew and the radiation source. That could mean water, polyethylene-rich materials, specialized structures, or other shielding approaches. But every kilogram you add has to be launched, accelerated, supported structurally, and paid for in fuel and design cost. So now the mission turns into a direct conflict between biology and propulsion. The crew needs mass to survive, but the ship is punished for carrying mass. Add more shielding and the vehicle gets heavier. Make the vehicle heavier and propulsion gets harder. Make propulsion harder and mission duration can increase, which increases radiation exposure again. Remove shielding to save mass, and the crew takes a higher dose. That is the trap. There is no cheap solution where you just line the walls with magic material and move on. Human deep space travel becomes a constant trade between acceptable exposure and acceptable mass, and both sides are ugly. And then there is the worst part. Galactic cosmic rays are especially difficult to deal with. These are not easy to stop with the kind of simple shielding people often picture. Some of these particles are so energetic that when they strike shielding material they can produce secondary particle showers. That means the shielding itself can sometimes create additional radiation effects instead of acting like a clean wall. So this is not just about putting more material in the way. The real problem includes particle energy, particle type, exposure time, shielding geometry, and what new particles may be created after impact. That makes time a major factor. In deep space, radiation does not just depend on where you are, it depends on how long you stay there. Every extra week, every extra month, every extra year is more exposure. That means mission duration is not just a scheduling issue, it is directly tied to biological damage. Slow missions may help with propulsion demands, but slow missions also give radiation more time to accumulate inside the crew's body. And this is not abstract. We already have measurements from missions beyond low Earth orbit showing that radiation exposure can become substantial. A Mars mission lasting on the order of 2 to 3 years is often discussed as a major concern for exactly this reason. Over that timescale, astronauts could receive radiation doses high enough to materially raise lifetime cancer risk. And cancer is not the only concern. Researchers have also worried about possible effects on the central nervous system and the cardiovascular system. So the danger is not just that someone might get sick decades later. The concern is that radiation may affect multiple body systems in ways that matter both during and after the mission. That point needs to stay clear, because people often treat radiation like a background number on a chart. It is not. Radiation can damage DNA, it can alter cells, it can increase long-term disease risk. It may also affect tissue types that are critical for cognition, circulation, and recovery. And unlike many engineering problems, you do not get to inspect the damage directly as it happens. The crew can be functioning, carrying out the mission, and still accumulating biological harm day after day. This is what makes deep space radiation such a hard limit. You cannot simply outsmart it with optimism. If you go fast, propulsion becomes harder and mass becomes more punishing. If you go slow, radiation has more time to do damage, so the mission is squeezed from both sides. Speed is expensive, slowness is biologically expensive, and the crew sits inside that trade. That changes how you should think about interplanetary travel. It's not just a long engineering project, it is a moving exposure problem. A mission to Mars is not only about getting there and back, it is also about how much radiation the crew absorbs during transit, during surface operations, and during the return. Every delay matters, every additional month matters, every propulsion compromise matters. Radiation turns time itself into a hazard. So the real implication is severe. Deep space is not just far from Earth, it is biologically toxic in a way that gets worse the longer you remain in it. Earth's atmosphere and magnetic field are doing much more for human survival than most people realise. Once you leave those protections behind, the crew enters as an environment where harmful particles become a constant operational fact, not an exceptional event. And because shielding costs mass, and mass punishes propulsion, the whole mission becomes a compromise between carrying protection and being able to move at all. And that leads directly to the next problem. Because even if you accept the radiation risk, even if you build a shielded spacecraft, and even if the crew survives the biological damage, you still run into the next major wall. Space is so large that even nearby destinations are separated by distances that turn every weakness into a bigger weakness. The environment is toxic, yes, but distance is what gives that toxicity time to do its work. Distance is where the whole idea starts breaking down at scale, because space is not just dangerous, it is so large that normal human ideas about travel stop being useful. On Earth, far usually means hours, maybe a full day, maybe a long flight across continents. In space, far means something much more serious. It means the time, risk, and system burden grow so much that the trip itself starts becoming the main problem. And this starts inside our own solar system, not between stars. The moon sounds close because we're used to hearing about it. But close in human language and close in space are not the same thing. The moon is about 384,400 kilometers, roughly 238,900 miles away. That is already far beyond anything in ordinary life. Mars is worse. Depending on where Earth and Mars are in their orbits, the distance can range from tens of millions of kilometers to more than 400 million kilometers. Neptune averages around 4.5 billion kilometers, about 2.8 billion miles, from the Sun. That is just one planet in our own system. So before anyone starts talking about star travel, the first thing to admit is that the solar system itself is already huge enough to break mission design. And this is where speed also stops sounding impressive. A spacecraft in low Earth orbit moves at around 7.8 kilometers per second, about 17,500 miles per hour. In everyday terms, that sounds extreme. It is vastly faster than a car, faster than a jet by a huge margin, faster than anything your body normally experiences as travel. But against cosmic distance, that speed is still weak. It is enough to circle Earth quickly. It is not enough to make the solar system feel small, and it is nowhere near enough to make interstellar travel feel realistic. The nearest star system, Alpha Centauri, is about 4.37 light-years away. 1 light-year is about 9.46 trillion kilometers. That number alone should reset the whole conversation. Human spacecraft are not on the edge of reaching the stars. They are not even close to making that kind of journey meaningful on human timescales. The best way to say it directly is this. Our fastest machines are still operating inside a very small local neighbourhood, and even that neighbourhood is already hard to cross safely with people on board. Then there is another problem. People underestimate. You do not just choose a destination and leave whenever you want. That is not how planetary travel works. The planets are moving. Earth is moving. Mars is moving. Efficient missions depend on orbital mechanics and launch windows. You wait for geometry that makes the trip possible with a realistic amount of energy and fuel, miss that window, and you're not just delayed by a few days. You can lose months and sometimes much more. So deep space travel is not only controlled by engineering, it is controlled by timing, built into the motion of the solar system itself. That means space does not give you roads, it gives you moving targets, and you have to leave at the right time, on the right path, with the right speed, carrying everything you need, because you may not get another practical chance for a long time. That makes human missions much less flexible than people assume. You're not just planning a trip, you're planning around celestial mechanics, and that removes a lot of the freedom people associate with travel. The next consequence is even worse, because distance does not just make the trip longer, it makes rescue and resupply weaker. On Earth, bad planning is often recoverable because logistics can save you. A replacement part can be shipped, extra supplies can arrive, specialists can be called in, help can move. In deep space, that ability shrinks fast. If something fails near Earth, you may still have some options. If something fails months away from Earth, you're mostly dealing with the consequences of your original design and whatever spare capacity you brought with you. Every extra kilometre matters because it adds more than just travel length. It adds communication delay, it adds isolation, it reduces rescue options. It increases the time that radiation, equipment wear, medical risk, and psychological stress have to build up. A failure on day 4 and a failure on day 400 are not the same kind of problem, even if the broken part is identical. The environment does not care that the crew has already invested months into survival. If a critical system fails far enough from Earth, the mission can become unrecoverable simply because the distance prevents outside help from arriving in any useful time. This is why even a Mars mission is not one challenge. It is many challenges locked together by distance. You need propulsion that can send a large human-rated vehicle there. You need life support that can keep working for many months. You need food, water, waste handling, spare parts, and medical capability. You need radiation management. You need psychological stability. You need a way to land safely on another world. You need systems that still work after the landing. And if the mission includes coming home, you need enough surviving hardware, enough fuel, and enough crew capability to reverse the process later. That is the real point. Distance forces all the problems to arrive together. On Earth, you can sometimes solve problems one at a time because support networks are nearby. In deep space, you have to solve almost everything in advance because you cannot count on fixing major mistakes after departure. There is no normal supply chain. There is no ordinary rescue. There is no quick return. The farther the destination, the more completely the mission has to be self-contained from the start. So the core shift in thinking is this. Space is not just a dangerous frontier. It is a geography so large that time, isolation, and system failure start combining into one larger threat. You're not dealing with a place that is hard because it is unfamiliar. You're dealing with distances so extreme that even successful missions become long, expensive, and biologically punishing, while failed missions become impossible to recover from. That changes the meaning of impossible. The issue is not that humans cannot move through space at all. The issue is that the distances between relatively survivable places are so large that the organism making the journey may not have enough endurance margin to cross them safely and still function on arrival. And once distance stretches the mission that far, the next problem becomes unavoidable, because the more time you spend travelling, the more another law closes in on you. Every kilogram of food, water, shielding, equipment, and life support adds mass. And once mass grows, propulsion stops being a detail and becomes a tyrant. That is where the mathematics of rockets starts crushing the dream directly. This is where the whole dream runs into math, and math does not care how inspiring the mission sounds. Rocket travel is not hard just because engineers have not tried enough. It is hard because the basic physics is punishing. The central problem is described by the Tsiolkovsky rocket equation. But the idea is simple even without the formula. If you want a spacecraft to gain a lot more speed, you usually do not need a little more propellant. You need a much larger amount. The increase is not gentle. It climbs fast. And that is where a lot of optimistic ideas start collapsing. This is the part people often miss. A spacecraft is not just carrying passengers. It is carrying everything needed to keep those passengers alive. And then it has to carry the fuel needed to move all of that, and then more fuel to move that extra fuel. That is the trap. Add radiation shielding, and mass goes up. Add food, and mass goes up. Add water, spare parts, medical gear, waste systems, and backup systems, and mass keeps going up. Add artificial gravity hardware, and it goes up even more. None of that mass is optional if the goal is long human survival. But every kilogram you add means the vehicle now needs more propellant to push it. And then the problem gets worse because propellant is also mass. So if you add more mass and then add more propellant to handle it, that new propellant also has to be accelerated. That means you need even more propellant again. This is why rockets look the way they do. They are mostly fueled with a much smaller useful payload at the top. That design is not just a style choice. It is the visible result of the underlying physics. A lot of the vehicle exists mainly to move the rest of the vehicle. That is why deep space human travel becomes so hard so quickly. The crew is light compared with the full mission system. The real mass comes from everything the crew needs around them. Pressure systems, oxygen, water, food, thermal control, shielding, structure, computers, power, spare parts, waste processing, and redundancy. A human mission is not a few people and some seats. It is a compact life-supporting environment, and rocket physics punishes that environment directly. Now look at chemical rockets. because they are impressive and still not enough for the kind of future people often talk about. Chemical propulsion is one of the great engineering achievements in history. It can launch payloads from Earth, place spacecraft into orbit, send probes across the solar system, and with careful planning it can support crewed missions to nearby destinations. But once you start talking about routine, fast, large-scale human deep space travel, chemical rockets hit serious limits. The issue is not that they are weak. The issue is that their exhaust velocities are too low for the scale of the job. In direct terms, chemical rockets burn through propellant quickly and deliver huge thrust, which is exactly what you need to escape Earth's gravity, but that does not mean they are efficient enough for fast, repeated, long-distance travel with heavy human payloads. They work, but the mass ratio becomes punishing. The farther, faster and heavier the mission gets, the worse the trade becomes. So chemical rockets are not a path to normal human expansion through space. They are powerful enough to start the trip, not powerful enough to make the universe feel accessible. Then there is staging, which is one of the cleverest solutions ever used in rocketry, and also one of the clearest signs of how severe the mass problem really is. A multi-stage rocket drops empty tanks and engines as it climbs. That way it no longer has to push dead weight after the propellant in that stage is gone. It is a brilliant solution. But notice what it says about the system. The practical way to reach space has often been to throw away most of the vehicle during ascent. That means even our best methods work by shedding mass aggressively because keeping all of it would be too expensive in propellant. So staging helps, but it helps by making the vehicle disposable. It does not remove the underlying problem, it just manages it. And that matters because once you start imagining reusable deep space human vehicles with heavy shielding and long-duration support systems, you are no longer dealing with a small payload riding on top of a launch stack. You're dealing with a very large mass that must be accelerated, maneuvered, possibly slowed down and maybe brought home again. Throwing away stages helps launch, but it does not magically solve the deeper problem of moving a human habitat across large distances. At this point, people usually bring up advanced propulsion, and that's fair, because better propulsion absolutely matters. Nuclear thermal rockets, electric propulsion, fusion concepts, and even antimatter ideas are often discussed for exactly this reason. Some of these approaches could improve the situation. Electric propulsion can be highly efficient. Nuclear thermal propulsion could offer better performance than standard chemical systems. Fusion, if it ever becomes practical for spacecraft, could potentially change the scale of what is possible. But none of this erases the central problem. Electric propulsion usually comes with low thrust, which is excellent for moving probes slowly and efficiently, but much harder to use when you need to move a heavy crewed system quickly. Nuclear systems bring engineering challenges and safety concerns. Fusion remains unrealized as a practical propulsion system for actual missions. Antimatter is even further from normal engineering use. So yes, advanced propulsion could improve the landscape, but it does not turn a massive, shielded, life-supporting human spacecraft into an easy thing to move. The question never goes away. Can this engine move a very heavy artificial environment fast enough, safely enough, for long enough to make the mission viable? That is the hidden reason the universe keeps feeling huge even as our technology improves. It is not just that we need better engines. It is that moving matter fast is fundamentally expensive, and humans are expensive cargo in the deepest physical sense. Not financially expensive, mass expensive. The body is fragile, so it needs support. Support needs hardware. Hardware needs structure. Structure needs shielding. Shielding adds mass. Mass needs propellant. Propellant adds more mass. The problem feeds on itself. And that is why the phrase human space travel can be misleading. It sounds like the task is to transport people. It is not. The real task is to transport a small artificial biosphere built to keep people alive, and then wrap that biosphere in enough propulsion capability to move it through an environment that punishes mass at every step. The rocket equation turns human vulnerability into a direct engineering penalty. The weaker and more dependent the passenger, the more infrastructure the vehicle has to carry, and the more brutally the math responds. So this section changes the argument in an important way. The universe is not huge only because of distance. It is huge because the cost of moving a survivable human environment rises so fast that each improvement in mission design is partly cancelled by the added mass required to keep the crew alive. That is why the problem is deeper than one missing invention. The challenge is built into the physics of propulsion itself, and once you do somehow push that mass to higher speed, the next problem gets even worse, because speed is not just useful, it is dangerous. The faster you go, the more acceleration hurts, the more stopping becomes a second propulsion problem, and the more even tiny particles out there become lethal on impact. Speed sounds like the solution, but once humans are on board, speed becomes another threat you have to survive. That is the next major problem. People hear that space is too far and the instant response is obvious: go faster. But speed only solves one part of the mission, the travel time. At the same time, it creates new stresses on the body, on the vehicle, and on the environment around the vehicle. A fast mission is not automatically a survivable mission. The first reason is simple. Humans are not just payload. They are living systems that react badly to force, shock, and prolonged stress. If you accelerate a spacecraft, the passengers feel that acceleration as a load on the body. If you decelerate, they feel it again. It is not enough for a ship to go fast in theory. It has to get to that speed in a way the crew can physically tolerate, and then it has to get rid of that speed without turning arrival into another medical emergency. That changes the problem immediately. You're not just trying to move a vehicle, you're trying to move a fragile biological crew inside it. Humans can survive high G loads for short periods under controlled conditions. Fighter pilots, astronauts during launch, test subjects in modern centrifuges. All of that shows the body can endure serious acceleration briefly, especially if the person is positioned properly and prepared. But that does not mean you can keep people under high acceleration for long periods. Even 2 to 3G sustained over time becomes exhausting and potentially dangerous. Blood distribution changes, breathing becomes harder, basic movement becomes harder, fatigue rises quickly, so the idea that you can just push a human spacecraft hard for long durations runs into a physiological limit very fast. That matters because it places a cap on how aggressively you can shorten a mission by acceleration alone. A short burst is one thing, a long push is another. If you want a fast trip across a serious fraction of the solar system, you do not just need a powerful engine. You need an acceleration profile that the passengers can survive without arriving injured, exhausted, or dead. So even before you deal with fuel, shielding, or navigation, the body itself is already telling you that speed has a biological cost. Then there is the part science fiction often leaves out, slowing down. Reaching a high speed is only half of travel. If you're going to another planet, moon, or station, arriving at extreme speed is useless unless you can reduce that speed safely. That means every plan built around rapid acceleration inherits a second problem of similar scale: deceleration. In practical terms, if you accelerate for a large part of the trip and then brake for the rest, your propulsion burden grows enormously. You're not doing one hard maneuver, you're doing two, with the crew and life support system operating the whole time between them. That is why interplanetary travel is not like a one-way sprint. It is acceleration, cruise, braking, possibly orbital insertion, and maybe later ascent and return. Every increase in speed makes the stopping problem bigger. So when someone says, just go faster, the real answer is, and then what will stop you? That is not a minor detail. It is a second propulsion crisis attached to the first one. Now, add the environment itself. At high speed, even very small particles become dangerous. This is already true in Earth orbit. Tiny debris moving at orbital speed can hit with enough energy to damage spacecraft surfaces, windows, radiators, or instruments. Something too small to notice in everyday life can act like a projectile in space because the relative speed is so high. And that is just in the speeds we already deal with. Push the vehicle faster and the hazard gets worse quickly. Dust and micrometeoroids are not just background clutter. In deeper space, they remain part of the environment. At tens of kilometers per second, a tiny grain can carry enormous kinetic energy. At much higher fractions of travel speed, the danger becomes extreme. So fast travel does not just reduce trip time, it makes the medium itself more hostile. The faster the ship goes, the more the space in front of it behaves like a field of potential impacts. That means shielding requirements rise, detection becomes harder, and the consequences of missing one tiny object become more severe. This is one of the least intuitive parts of the whole subject. People think of empty space as giving you room to move safely. But once velocity gets high enough, emptiness is not good enough. A few particles, a bit of dust, a small fragment, any of that can matter because the energy of impact rises so sharply with speed. So in trying to outrun the problems of time and radiation, you can create a new impact problem that is just as serious. The vehicle itself also suffers more as performance rises. Launch already puts spacecraft structures under major stress. Tanks, engines, guidance systems, and the crew compartment all operate close to demanding limits. Re-entry already requires careful thermal protection because high-speed interaction with an atmosphere creates enormous heat. Even without atmospheric re-entry, high-energy trajectories and aggressive maneuvers place tighter demands on structural integrity, vibration tolerance, thermal management, navigation precision, and control authority. The faster you try to move a human-rated spacecraft, the less room there is for error. That is especially severe for crewed missions because the standard is not merely reaching the destination. The crew has to arrive alive, pressurized, hydrated, functional, and capable of continuing the mission. A robotic probe can fail partially and still return useful data. A human mission is much less forgiving. A small navigation error, a structural weakness, a thermal problem, a missed deceleration window. Any of these can destroy the mission because the cargo is not hardware alone. It is a living crew that needs a narrow range of conditions to keep functioning. So speed creates a paradox. You need more of it because long missions mean more radiation exposure, more consumable use, more equipment wear, and more psychological strain. But as you demand more speed, propulsion needs go up, impact risk goes up, stopping becomes harder, structural requirements get stricter, and physiological tolerance becomes more important. In other words, speed is both part of the solution and part of the danger. That is why the idea of just building a faster ship is too simple to survive contact with reality. A vehicle fast enough to make deep space travel feel reasonable has to accelerate without destroying its passengers, survive impacts with tiny particles, manage the structural and thermal consequences of high performance, and then decelerate safely at the destination. Every one of those requirements adds mass, complexity, risk, or all three. So the same tool you need to make the trip practical also makes the mission harder to survive. That is the real speed paradox at the center of human spaceflight. Fast enough to matter is hard to survive, and slow enough to survive may be too slow to matter. If you go slowly, the mission drags on and everything else gets worse. If you go faster, the physical and biological burden of doing that safely starts rising toward another limit. Speed is not freedom. It is another tightly constrained system problem. And once you realize that, the next wall gets even harder to ignore. Because even if the ship can move at the right speed, and even if the crew survives the acceleration and the impacts, the mission still depends on a more basic requirement. The spacecraft has to keep humans alive day after day, month after month, in a sealed environment where even breathing creates a problem that the vehicle must constantly reverse. Life support sounds like a support system, but in a deep space mission, it is really the mission underneath the mission. The spacecraft is not just a vehicle with some survival equipment attached. It is a sealed environment that has to keep a small group of humans chemically stable for months or years. On Earth, life support is mostly invisible because the planet does it for free. The atmosphere gives you oxygen, plants and oceans help regulate gases, water cycles through the environment, waste is absorbed by huge natural systems, and temperature stays inside a range your body can handle with clothing and shelter. In space, none of that exists unless the spacecraft creates it. That means the ship has to do much more than move. It has to manage oxygen generation or oxygen storage, remove carbon dioxide, recover water, process waste, control humidity, remove trace contaminants from the air, store or possibly produce food, and regulate temperature. Every one of those is part of staying alive. If one of them fails badly enough, the crew is in danger even if the engines are working perfectly and the trajectory is exactly right. That is why life support is not a gadget. It is a closed ecological problem forced into hardware. A good example is carbon dioxide. Most people focus on oxygen because it is the obvious thing you need to breathe, but oxygen is only half the problem. Every time you exhale, you're putting carbon dioxide into the cabin air. In a spacecraft, that means the crew is constantly contaminating its own environment just by being alive. If the carbon dioxide removal system starts underperforming, the gas can build up. That can lead to headaches, slower thinking, fatigue, poor decision-making, breathing distress, and eventually much more serious consequences. It is not dramatic in a cinematic way, but it is one of the most real dangers in a sealed habitat. Your own metabolism becomes a continuous source of atmospheric pollution, and the ship has to reverse that process without stopping. That point matters because it shows how little margin there really is. On Earth, a room with stale air is unpleasant. In deep space, a closed cabin with rising carbon dioxide becomes a direct threat to mission performance and crew survival. So the crew is not just depending on the ship for transport. It is depending on the ship to keep the chemistry of the air inside a narrow, safe range all the time. That is not optional. That is as basic as breathing itself. Then there is water. And water is one of the clearest examples of how mass and survival collide. Humans need water for drinking, hygiene, food preparation, and sometimes thermal control and other life support functions. A litre of water has a mass of about 1 kilogram, or 2.2 pounds. That sounds manageable until you multiply it by several crew members, then by days, then by months, then by safety margin and redundancy. Very quickly, water becomes a major payload category. You're not carrying a few bottles, you're carrying a large mass of a survival-critical substance that the crew cannot do without. That is why recycling is essential. Space missions already depend heavily on water recovery systems because launching endless fresh supplies is not practical. But the deeper problem is that recycling is not magic. It depends on machinery, filters, power, maintenance, contamination control, and a design that keeps working over long durations. Perfectly closed water recycling over years is extremely difficult. Losses happen, wear happens, failures happen, so a long mission has to balance stored water, recycled water, and contingency planning, and all of that adds complexity and mass. Food seems simpler at first, but it is not. Food is not just calories in containers, it has shelf life. Nutrients degrade over time, vitamins do not remain equally stable forever. Packaging builds up as waste. Monotony affects whether people want to eat enough to stay healthy. Morale is connected to food more than people often admit. A crew on a long mission is not just carrying meals, it is carrying a long-term nutritional system that has to remain safe, adequate, psychologically tolerable, and resistant to spoilage or contamination. And if someone says, then grow food on board, that brings in a whole new level of difficulty. Growing food means lighting, water distribution, nutrient management, microbial control, waste handling, crop reliability, and disease control. It means part of the spacecraft starts acting like a farm. That may help in some future systems, but it does not simplify the mission. It adds another interdependent subsystem that can fail, drift, or consume resources unexpectedly. So even food, one of the most ordinary needs on Earth, becomes a major systems engineering problem once you leave the planet. Now add redundancy, because no rational mission design would trust a single machine with something this important. If life support is critical, then you need backup systems, spare parts, maintenance tools, fault detection, repair procedures, and crew members trained to manage failures. But every backup adds mass. Every extra machine adds more parts that can break. Every spare part takes volume and planning. Every diagnostic tool and maintenance task adds work to the crew, so redundancy keeps the mission alive, but also makes the spacecraft heavier and more complex. That creates another trap. You need life support systems to keep the crew alive. Then you need backup life support systems in case the first ones fail. Then you need the ability to repair both. Then you need enough power, cooling, and structural support for the entire set of systems, so the spacecraft becomes a dense network of interdependent loops: air, water, waste, thermal control, filters, power, diagnostics, spheres, and procedures, all of which must keep working in a hostile environment for a very long time. And they have to do this after launch loads, during exposure to radiation, under constant operational wear, and while being maintained by the same crew whose survival depends on the system working. That is the hidden truth people often miss. Propulsion is not the only hard part. In some ways, it's not even the most relentless part. A ship does not fail only when the engine stops. It fails when it can no longer function as a human habitat. If the air becomes unsafe, if the water system degrades beyond recovery, if contaminants build up, if food quality drops too far, if thermal control slips, the mission can be in serious danger even while the spacecraft is still moving exactly as planned. So the real challenge is not just sending a crew through space. It is building a small artificial world that can remain stable while cut off from Earth for a long time. That is a much harsher requirement than people usually imagine. It means the vehicle is not merely transporting humans. It is temporarily replacing pieces of an entire planetary support system. And that is why life support is not a side module you bolt on after the exciting parts are done. It is a permanent ecological crisis in a box that has to be managed every hour of the mission. And once you accept that, the next problem gets even darker, because even if the spacecraft keeps the crew alive chemically, and even if all those systems keep running, the human body can still fail in ways that the ship is poorly equipped to treat. The farther you go from Earth, the more medicine stops being modern medicine and becomes controlled improvisation with almost no backup. Medicine is where a deep space mission stops looking advanced and starts looking fragile, because no matter how good the spacecraft is, you cannot bring a real hospital with you. On Earth, serious medical problems are survivable partly because you are surrounded by infrastructure. You have imaging, labs, blood supply, specialists, sterile operating rooms, intensive care, pharmacies, and emergency evacuation. If one doctor cannot solve the problem, another one can. If one hospital cannot handle it, the patient can be transferred. In deep space, almost all of that disappears. What remains is a limited stock of equipment, a limited stock of drugs, delayed communication with Earth, and whatever medical training the crew already has. That changes medicine completely. Treatment is no longer based on the full resources of civilization. It is based on what a small crew can do in a hostile environment with tight mass limits and no outside rescue. You're not practicing modern medicine in space. You're practicing a reduced version of medicine, with fewer tools, fewer people, less flexibility, and far worse consequences if the first decision is wrong. That is why the medical side of deep space travel is not a detail. It is another hard limit on how far humans can realistically go. This becomes obvious the moment you stop thinking only about traumatic accidents and start thinking about ordinary human problems: a kidney stone, a dental infection, appendicitis, a dangerous heart rhythm, a blood clot, an eye problem, a fracture, severe allergic reaction, or a psychiatric crisis can all be serious on Earth. In deep space, any one of those can become a mission-level emergency. Not because the condition is automatically worse in space, but because the response options are so much weaker. A problem that would normally be manageable inside a large medical system becomes much more threatening when there is no hospital, no specialist, no surgery team, and no fast return. This is exactly why astronauts are medically screened so heavily before missions. The system is trying to lower risk in advance, because it knows treatment options later will be limited. That alone should tell you something important. Human biology is not reliable enough to assume years of perfect health just because the crew was healthy at launch. People get sick. Bodies produce surprises. Small issues can turn into larger ones. Deep space mission design has to assume that medicine will be needed, but the mission also has to admit that its medical capacity will always be incomplete. Now consider surgery, because this is where a lot of assumptions break immediately. Surgery in microgravity is not the same as surgery on Earth with smaller equipment. Fluids do not stay where you want them. instrument handling changes. Keeping a sterile field becomes harder. Stabilizing the patient becomes harder. Anesthesia is more complicated. Monitoring becomes more complicated. If something goes wrong during the procedure, there is no operating room down the hall, no full surgical team arriving to help, no intensive care unit ready to take over afterward. So even if a crew member has strong medical training, they are still working inside a vehicle that was not designed to function like a modern hospital. They are treating a patient in a place where space, equipment, blood products, sterile capacity, and support staff are all limited. That is the core reality. Medicine off Earth is not just medicine performed farther away, it is medicine after a large part of the normal medical system has been removed. And diagnosis gets harder too, because bodies in deep space are not behaving exactly like bodies on Earth. Fluid shifts, muscle loss, bone changes, radiation exposure, poor sleep, stress and confinement can all change what normal looks like. That means symptoms may not point as clearly to the right diagnosis. A sign that means one thing on Earth may mean something different in space, or may be harder to interpret because the person's baseline physiology has already changed during the mission. The farther the crew goes, the more they have to rely on medical autonomy, and autonomy in medicine becomes dangerous when the available tools are limited. This also matters because communication delay makes consultation slower and less useful. In low Earth orbit, support from the ground can still be close to real time. Farther away, that disappears. On a Mars mission, for example, communication delay means you cannot have instant back and forth guidance during an emergency. The crew may have to make decisions before outside experts can respond, and that means the mission is relying on local judgment under stress, often with incomplete data. That is not how high-level medicine is supposed to work. It is a fallback condition, and in deep space it becomes normal. Then there is the broader issue people often avoid, long-term population biology. It is not enough to keep healthy adults alive temporarily, and this is where the uncertainty gets much larger. We do not have anything close to a complete answer for how human development would function over generations away from Earth normal conditions. That is a much harder problem than sending trained adults on a mission. Adults can be screened, selected, trained, and medically supported for a defined period. A multi-generational population is different. It must survive normal life events, developmental stages, chronic illness, injury, disability, aging, and emergency care without relying on Earth to solve every serious problem. That is not a small extension of current space medicine. That is an entirely larger category of challenge, and it remains far from solved. This is what breaks the fantasy of casual settlement. A true settlement is not just a habitat with people inside it. It is a place where illness, injury, pregnancy, aging, disability, surgery, emergency care, and long-term health management are all possible as part of normal life. If a colony cannot handle ordinary biological events without rescue from Earth, then it is not a stable civilization. It is a medically fragile outpost that survives only while external support continues. That is the real medical conclusion. You cannot pack enough safety to turn deep space into a place where medicine works like it does on Earth. You can reduce risk, you can screen crews, you can carry drugs, instruments, and diagnostic tools, you can train people very well, but you cannot fit the full protective network of modern healthcare into a spacecraft without running into the same old enemies: mass, complexity, and limited volume. So medicine in deep space is primitive by definition, not because the people are unskilled, but because the infrastructure that makes medicine powerful on Earth cannot fully travel with them. And once that is clear, the next problem becomes more dangerous in a different way. Because even if the crew stays physically healthy enough, the mission still depends on something more fragile than hardware. Long isolation, delayed communication, confinement, and constant risk do not just test machines. They test the mind, and in deep space the human mind becomes part of the survival system. Isolation is not a side issue in deep space, it is one of the systems the mission depends on surviving. People often talk about engines, radiation, food, or life support as if the human mind is just along for the ride. It is not. In a deep space mission, psychology becomes part of the engineering problem. The crew is living inside confinement, monotony, danger, delayed communication, restricted privacy, and constant dependence on a few other people. Outside the hull is an environment that can kill them immediately. Inside the hull, the mission still has to continue on schedule. That means the brain is not an optional passenger. It is part of the life support chain. That changes the whole way you should think about long missions. A deep space crew is not just trying to stay calm, it is trying to remain functional under pressure for months or years. People have to make technical decisions, maintain equipment, monitor health, solve problems, manage conflict, and keep routines stable, while living in a place with very little variety and very little escape. On Earth, stress is often buffered by movement, social choice, fresh environments, and infrastructure. In space, many of those buffers disappear. The mission does not pause because someone is mentally drained. Communication delay makes this much harder. Near Earth, support from the ground can still feel immediate. At the Moon, communication is close enough to real time that normal conversation is still possible by human standards. At Mars, that changes completely. One-way communication delay can range from about 4 to 24 minutes depending on where the planets are in their orbits. That means normal conversation disappears. You cannot ask a question and get an answer right away. You cannot have a real-time argument, reassurance, or crisis discussion with Earth. You send a message, then you wait. That waiting matters more than people think. Humans are built around responsive connection. In danger or uncertainty, people naturally reach out, expect feedback, and regulate stress through real-time interaction. Deep space communication delay cuts through that reflex. If something goes wrong, technical or emotional, the crew may not be able to lean on Earth in the way human beings normally lean on other people. Support still exists, but it arrives slowly. That means fear, doubt, conflict, and uncertainty sit in the cabin longer before outside help can even respond. Then there is monotony and confinement, and this is not a small comfort issue. Analog missions in remote environments, polar stations, submarines, isolation studies, and actual long-duration orbital missions all point to the same basic concern: confinement changes people. Mood can shift, sleep can worsen, cognitive sharpness can fluctuate, social friction can grow, performance can suffer. The problem is not just boredom. The problem is that high-stakes technical work still has to be done under conditions of low variety, low privacy, repeated routines, and permanent dependence on the same small group. That means even minor interpersonal problems can become serious over time. On Earth, people can leave the room, go outside, see different faces, or change environments. In a deep space mission, those normal pressure release mechanisms are limited or absent. A small irritation can become a recurring stressor. A mismatch in work style can become a long-term strain. A conflict that would normally fade can keep resurfacing because the people involved cannot truly separate. So team dynamics are not a soft issue. They're a mission stability issue. Now, some people answer this by pointing to the sense of wonder astronauts often describe. That is real. Seeing Earth from space can produce profound emotional responses, a shift in perspective, a strong sense of fragility and scale. Sometimes this is called the overview effect, but that does not cancel the rest of the psychological burden, or can exist at the same time as fatigue, grief, conflict, loneliness, anxiety, or depression. A beautiful view does not repair a damaged team relationship. A powerful moment of perspective does not remove sleep deprivation or chronic stress. That is important because the romantic picture of space psychology often uses wonder as if it were a protective force. It is not. The mission still runs on habits, judgment, stability, cooperation, and mental resilience. If those start degrading, the fact that the crew is also experiencing awe does not solve the operational problem. Deep space missions do not fail only from panic or breakdown. They can also fail from slower psychological erosion, less focus, more friction, weaker decision-making, and reduced emotional margin. Autonomy makes that load even heavier. The farther you go, the more the crew has to manage on its own. They are not only travellers, they are also maintainers, medics, emergency responders, technicians and decision makers. They have to solve mechanical issues, monitor their own health, respond to unexpected events, and support each other emotionally because there may be no one else available in real time. That sounds capable and disciplined, and it is, but it is also a large psychological burden over long periods. This matters because self-management is effort. Supporting other people is effort. Constant vigilance is effort. Living under risk without real escape is effort. On a short mission, highly trained people may absorb that load. Over much longer periods, the weight accumulates. The crew is not just carrying out tasks. It is also carrying the awareness that if they fail technically, medically, or socially, there may be no one who can step in fast enough to save the situation. That is not just responsibility, it is chronic psychological pressure. There is a common response here, which is that astronauts are exceptional people. That is true. Crews are heavily screened, heavily trained, and selected for exactly these kinds of pressures. Some individuals may cope remarkably well, but that leads to a different conclusion than the one many people want. If deep space travel only works for tiny numbers of unusually selected people under extreme preparation, then it is not evidence that humans in general are suited for large-scale space travel. It suggests the opposite. It suggests that only rare individuals may be able to function in that environment at all. And that changes the meaning of the whole project. There is a difference between saying a handful of exceptional people can survive a mission and saying humanity can travel through space as a normal extension of civilization. Those are not the same claim. If the only workable model depends on rare crews with extreme screening, rigid discipline, and years of preparation, then deep space travel is not a broad human future. It is a narrow, elite edge case. That is the deeper conclusion of this section. Isolation does not just stress people in a general way, it directly affects the reliability of the mission, because human judgment, cooperation, attention, and emotional stability are part of what keeps the spacecraft functioning. The mind is not separate from survival. It is one of the systems being pushed toward its limit. And the farther from Earth you go, the less outside help can reduce that pressure. And then the next problem raises the stakes again, because even if the crew gets through the isolation, even if the team stays functional, and even if the ship survives the journey, reaching another world does not mean the danger is over. In many ways, arrival is where the mission becomes even more unforgiving, because other planets and moons are not destinations waiting to receive you. They are hostile environments that start creating new failure modes the moment you get there. Arrival is not success in space. It is the start of a second survival problem. That is one of the biggest gaps between how people imagine space travel and how it really works. Reaching another planet or moon does not mean you are safe. It means you now have to enter an alien environment, descend through it or onto it, land without destroying the mission, survive on the surface, and in many cases launch again later. Every one of those steps can fail. So getting there is only half the problem, and sometimes not even the harder half. That is because every world gives you a different set of hazards. Some have almost no atmosphere, some have toxic atmospheres. Some have enough atmosphere to create heating and drag during entry, but not enough to make landing easy. Some are extremely cold, some have weak gravity, some have crushing pressure, some have dangerous terrain, dust or radiation. There is no general-purpose planet arrival solution that makes all of this easy. Every destination creates its own set of problems, and each of those problems has to be solved by hardware that survived the journey there. Mars is the most common example because it is often treated like a future backup Earth. But Mars is not Earth-like in the ways that matter most for human survival. Its atmosphere is only about 1% of Earth's surface pressure. That is far too thin to breathe, far too thin to provide strong protection from radiation, and thick enough to create serious entry and landing complications. This is one of the most awkward combinations in the solar system from an engineering point of view. The atmosphere is not thick enough to make landing easy the way it can on Earth, but it is thick enough that you still have to deal with aerodynamic heating and complex descent problems. The surface environment does not help. The average temperature on Mars is around minus 63 degrees Celsius, about minus 81 degrees Fahrenheit. Liquid water is not just sitting around in a convenient form for humans to use. The planet has dust, cold, radiation, and a pressure so low that you still need a pressurized habitat just to exist outside your suit. So even on the planet most often marketed as humanity's next home, survival still depends on artificial pressure, thermal management, reliable power, spare parts, life support, and a level of industrial capability far beyond just planting a flag and setting up a shelter. That already tells you Mars is not a second Earth. It is a harsh operating environment where everything basic has to be manufactured or maintained actively. Air is not breathable, warmth is not available, pressure is not available, radiation protection is weak, water access is difficult. So the phrase going to Mars often hides the harder reality, which is building and sustaining a functioning artificial habitat on a world that does not naturally support your body. Then there is gravity, and this is another place where people assume more than we actually know. Mars has about 0.38 g. The Moon has about 0.16 g. Those are not zero, but they are far below Earth's 1 g, and we do not yet know whether partial gravity is enough to protect humans from long-term bone loss, muscle wasting, cardiovascular change, developmental problems, or other effects tied to reduced loading. That uncertainty matters a lot. It means another world might feel easier than microgravity, but still not be enough to keep the body healthy over long periods. So having ground under your feet is not automatically a biological solution. A person may be able to stand, walk, work and survive there for some period of time, but still suffer slow damage because the local gravity is too weak to maintain normal human physiology. That means another planet can feel more stable than a spacecraft and still remain fundamentally bad for the body. In other words, surface presence is not the same as long-term habitability. Dust makes this even worse, because on worlds like the Moon and Mars, dust is not a small inconvenience. It is a systems problem. Fine dust can get into seals, joints, bearings, aerolocks, suits, tools and machinery. It can abrade surfaces. It can contaminate equipment. If it is brought into habitats or inhaled, it may become a health issue. It can coat radiators, degrade thermal performance, reduce the efficiency of solar panels, and complicate maintenance in ways that slowly wear the mission down. Apollo astronauts reported how persistent lunar dust was, how it clung to suits and entered the cabin. That was on brief missions close to Earth. For long surface operations, dust becomes a constant enemy. This matters because it attacks the interfaces of the mission, the places where equipment has to move, seal, connect, and remain clean enough to work. A world can be reachable and still be operationally hostile at every surface contact point. That is a very different situation from exploring difficult environments on Earth, because on Earth, corrosion, dirt, and wear happen inside a larger support network. On another world, the same problems happen inside a very fragile system with limited spares and limited repair options. Now add the final surface problem that people often treat like an afterthought leaving. Landing humans somewhere is not enough if the mission requires them to come home. Returning to orbit is another full engineering event. On Mars, for example, you need an ascent vehicle that still works after a long stay in cold, dust, reduced gravity, radiation, and maintenance-limited conditions. You need fuel or fuel production. You need functioning avionics, engines, seals, and structures. You need a crew that is still healthy enough to operate the system. You need all of this after months of exposure. Where? That means departure is not a small detail at the end of the story. It is a second escape mission that depends on hardware surviving another world and on people surviving the strain of living there. If a key system degrades too much, if contamination spreads where it should not, if the crew is too weakened, if the ascent stage fails, then the mission does not become difficult. It becomes final. There is no roadside rescue on Mars. There is no practical emergency retrieval from another world once the situation collapses. That is the real point of landing in space. On Earth, exploration often treated landfall as the end of the hardest part. In space, landfall begins another phase where the environment keeps attacking you from new angles. Another world is not a destination in the normal sense. It is a hostile work site where pressure, temperature, dust, gravity, radiation, and machinery all remain active threats. The journey does not end when the crew arrives, it changes form. And that raises the next problem even further, because once missions become that long and that complex, failure stops being about one dramatic disaster. It becomes about time. The longer the journey lasts, the more small risks pile up, the more parts wear down, and the more likely it becomes that something somewhere will go wrong simply because enough time has passed for the math to turn against you. Time is what turns a hard mission into a losing mission, because long-duration space travel is not just about surviving danger once, it is about surviving thousands of smaller dangers over and over until one of them finally matters. On a short mission, a lot of weaknesses can stay hidden. A system can run a little hot, a part can wear a little faster than expected, procedure can be a little inefficient, and the crew can still get home before those problems fully develop. On a long mission, that margin disappears. Time keeps pulling on every weakness until something gives. That is why long missions are really reliability wars. A component that is 99.9% reliable sounds excellent when you hear the number by itself. But a real spacecraft is not one component. It is thousands of components, many of them running continuously, many of them cycling repeatedly, many of them interacting with each other. Stretch that over months or years, and the math gets worse. A tiny failure chance repeated enough times stops feeling tiny. Human space travel is not only threatened by major disasters, it is threatened by the accumulation of enough minor failures, enough wear, enough drift, and enough imperfect systems operating for too long. That changes the whole way you should think about safety. The mission is not just trying to avoid one explosion or one dramatic accident, it is trying to survive a long chain of ordinary degradation. Filters clog, seals age, electronics degrade, lubricants behave differently in space, batteries cycle and lose performance, tanks and structures experience fatigue, software develops problems, sensors drift out of calibration, valves stick, microbial growth happens where it should not. None of these things sound like cinematic disasters by themselves, but over long durations, they're exactly the kinds of problems that wear a mission down. On Earth, these kinds of failures are often manageable because they happen inside a civilization that absorbs them. There are spare parts, technicians, suppliers, experts, clean rooms, machine shop, and shipping networks. In deep space, the crew becomes the supply chain. That is the serious shift. Every repair takes crew time, every repair uses tools, every repair consumes spare parts that cannot easily be replaced. Every repair also costs attention, energy, morale, and future contingency margin. So maintenance is not something you do occasionally when a problem comes up. On a long mission, maintenance becomes a permanent condition of survival. That matters because it means the spacecraft is slowly turning its reserve capacity into ordinary operating cost. Every time the crew spends a part, uses a backup, patches a workaround, or adapts to degradation, the mission loses some of its ability to handle the next problem. Even a successful repair can weaken the mission overall if it consumes resources that were meant for later emergencies. So a long-duration mission is not simply about whether the crew can fix things, it is about whether the crew can keep fixing things without running out of time, tools, spares, and mental bandwidth. Redundancy helps, but it does not solve this forever. You can duplicate critical systems, and any serious mission has to do that. You want backup pumps, backup electronics, backup filters, backup computers, backup procedures, but you cannot duplicate everything without limit. At some point, the mass penalty becomes too high, the complexity becomes too large, and the added systems themselves become more things that can fail, so redundancy is necessary. But it is not infinite protection. It is another trade. That means long-duration human spaceflight is not a perfect safety problem. It is a probability management problem. You're not proving that nothing will fail. You're trying to design a system where failure remains survivable long enough to finish the mission. But the longer the mission lasts, the worse that probability picture becomes. You cannot pack every spare. You cannot predict every failure mode. You cannot assume every repair will work under stress. Eventually, the curve starts bending against you. And machines are not the only things that wear down over time. Human performance degrades too. Fatigue builds up, sleep quality matters, stress matters. Repetition can produce complacency. Small burdens that are tolerable for a week or a month can become much harder after hundreds of days. A crew that has already spent months dealing with routine maintenance, minor alarms, disrupted sleep, tight schedules and low-grade stress is not the same crew that launched. They may still be highly capable, but their cognitive and physical margin may be smaller than before. This matters because machines do not fail in isolation. They fail in the hands of people who must notice the warning signs, diagnose the cause, choose the response, and carry out the repair correctly. If the crew is tired, stressed, distracted, or less mentally sharp, then the same technical problem becomes more dangerous. So time does not only degrade hardware, it degrades the human ability to respond to hardware problems. That is a multiplier most people underestimate, and that is exactly the broader point. Time amplifies every other problem in the mission. Radiation dose grows with time, psychological strain grows with time, medical risk grows with time, food and water reserves shrink with time, equipment wear grows with time, maintenance burden grows with time. So time is not just another factor on the list, it is the thing that makes the whole list heavier. That is why distance is so destructive. Distance forces long travel time, and long travel time gives every weakness more room to act. This is also the point where optimism often becomes misleading. People like to think of a failed mission as bad luck, a rare accident, something that happened because one thing unexpectedly went wrong. Sometimes that is true, but as mission duration grows, another possibility becomes harder to ignore. Failure may stop being unusual. It may become the statistically normal result of enough complexity, enough exposure, enough wear, and enough time operating away from support. In other words, the problem may not be that one mission got unlucky. The problem may be that the mission design was living on borrowed probability the whole time. That is a very uncomfortable conclusion, but it follows directly from the logic of long-duration spaceflight. If enough systems must work, enough people must remain healthy, enough supplies must last, and enough repairs must succeed over a long enough timeline, then eventually the chance of getting all the way through without a serious breakdown starts dropping towards something much worse than people want to admit. At enough duration, failure is no longer surprising. It is built into the statistics. And that raises the next level of the argument, because if missions inside our own solar system already get pushed toward these limits by time, then interstellar travel does not just look harder. It starts breaking the entire concept of a normal human mission. The distances are so large that the timescales stop fitting inside one life, and once that happens, the whole idea of humans simply boarding a ship and going to another star starts falling apart. Interstellar travel is not just a harder version of going to Mars. It may be the point where the idea of a normal human mission stops making sense at all. The reason is simple. The nearest stars are still unbelievably far away by human standards. Alpha Centauri is about 4.37 light-years away. That sounds compact because the number is short, but the real scale is extreme. It is more than 41 trillion kilometers, or over 25 trillion miles. Those are not just big numbers. They are mission-destroying numbers once human lifetimes are part of the calculation. This becomes obvious the moment you compare that distance to the speeds we actually know how to reach. Around 17 kilometers per second is already extremely fast in human terms. That is faster than almost anything people ever experience directly. But against interstellar distance, it is almost useless. At that kind of speed, a trip to Alpha Centauri would take on the order of tens of thousands of years. That is not a long mission. That is a time scale so large that the idea of a crewed voyage breaks immediately. No life support system lasts that long. No crew remains a crew over that length of time, so people usually jump to futuristic speeds. Fine, suppose you somehow reach 10% of light speed, around 30,000 kilometers per second. That sounds like it solves the problem, but it does not solve it cleanly. Even at that speed, a one-way trip to Alpha Centauri is still more than 40 years, and that is before you count acceleration and deceleration. So now ask the real questions. What engine gets a massive human-rated vehicle to that speed? What power source feeds that engine? What shielding survives travel through interstellar dust at that velocity? What habitat remains functional for decades? What medical system handles a mission that long? What impact protection stops tiny particles from becoming destructive at those speeds? That is the deeper point. Once you start talking about serious fractions of light speed, you are not just asking for a better spaceship. You're asking for a complete system that can move an artificial human environment at speeds far beyond anything we currently know how to do with people. And as speed rises, all the old problems get worse: propulsion, impact risk, shielding, structural stress, life support duration, and failure consequences. So even futuristic velocity does not make interstellar travel normal. It just moves the impossibility into more advanced parts of the engineering. Then there is relativity, which people often mention as if it rescues the idea. Yes, time dilation becomes important at high enough fractions of light speed, but this is usually misunderstood. Relativity does not make the engineering easier. It only becomes helpful after you have already achieved enormous velocity, which is exactly the part we do not know how to do for a human habitat. In other words, relativity may change the experience of time for travelers at extreme speed, but it does not remove the need to build a vehicle, power it, protect it, and accelerate it to that speed in the first place. So saying relativity helps is not wrong, but it misses the real problem. The barrier is not that physics forgot to include a clever effect that shortens the trip. The barrier is that getting into the regime where that effect matters is already beyond the practical reach of human space engineering as we understand it. The universe is not denying you a shortcut. It is charging an enormous price to even get close to one. At that point, the mission starts changing category. If the travel time is longer than a human lifetime, then it is no longer a voyage in the usual sense. It becomes something else. It becomes a generation ship or some equivalent form of moving society. That means the problem is no longer just fuel, shielding, and navigation. Now you need governance, education, food production, medicine across generations, social stability, repair capability, cultural continuity, and a way to make sure the descendants of the launch crew are still willing to continue a journey they did not choose. That is a completely different kind of challenge. The people who arrive are not the people who left. The mission has turned from transportation into civilization transport. And that means human interstellar travel is no longer about moving astronauts to another star. It is about maintaining a self-contained society inside a machine for decades, centuries, or longer, depending on the speed. That is not a larger spaceship problem. That is a gamble on whether a sealed traveling civilization can remain stable long enough to finish the trip. Then people reach for the usual science fiction escape, suspended animation, cryo-sleep, or some kind of practical freezing and revival. But that is not a solved option. Human tissue, especially the brain, does not tolerate simple freeze and revive treatment without catastrophic damage. Research and preservation exists, and it may matter for some medical contexts, but it is nowhere near turning interstellar crew transport into an engineering project you can start planning seriously around. The concept remains popular mostly because it offers a way to avoid confronting the timescale problem directly. So when you strip away the shortcuts that are not actually available, the core conclusion gets sharper. The phrase human mission to another star may itself be the wrong category. Not just premature, not just difficult, but mismatched to the actual scale of interstellar space. Once the distances become that large, the thing that travels may no longer be a normal crewed mission in any recognizable sense. It may be a robotic probe, a seed bank, a machine civilization, a digital archive, a generation-bound social experiment, or something else entirely. That is the part most people resist, because the classic image is so powerful: humans boarding a ship, crossing the stars and arriving somewhere new. But the scale of the universe may not fit that image. The body is too fragile, the support systems are too heavy, the trip times are too long, and the engineering demands become too extreme. The farther you push the mission, the less it resembles a human journey, and the more it starts resembling a different kind of entity being sent outward. And that leads straight into the next illusion, because even if someone accepts that interstellar travel is too much, they often fall back on colonizing nearby space as the solution to humanity's future. But that idea has its own problem. Building settlements off Earth does not remove the burden of human weakness. It takes all the same biological, ecological, medical and engineering problems and relocates them into even harsher environments. The idea of colonizing space sounds like a solution, but most of the time it's just a way of moving Earth's problems into places that are even less forgiving. That is the problem with the escape planet story. It sounds strategic, like becoming multiplanetary automatically makes the species safer. But that skips the arithmetic. Earth supports billions of people because Earth is doing an enormous amount of work for free. It provides atmosphere, liquid water, pressure, magnetic shielding, ecosystems, soil cycles, climate regulation, and huge natural energy flows. None of that comes standard on the Moon, Mars, or in orbital habitats. So when people talk about building a second home for humanity, they're usually not talking about moving civilization to another Earth. They're talking about building sealed artificial environments that imitate small pieces of Earth well enough to keep people alive. That is a completely different thing. You're not relocating civilization into a naturally habitable world. You're suspending parts of civilization inside hardware that must keep working continuously in an environment that is actively hostile. The next problem is scale, and scale is where the fantasy usually starts breaking. A research base with a few people is one thing. Maybe with enough money and engineering you can imagine a settlement with dozens or perhaps hundreds under very optimistic conditions, but replacing any meaningful fraction of Earth's population is a different category entirely. Even moving 1 million people off Earth with enough habitat volume, life support, food systems, medical support, energy systems and industrial tools would require an industrial effort so large that most discussions simply skip over it, and moving them is only the beginning. Once people arrive, they still need an economy. They still need medicine, housing, governance, manufacturing, printing, education, waste handling, repair capability, and some level of social stability. A settlement is not real just because it has walls and air inside. It has to function across normal life, not just survival on paper. That means the colony has to support work, illness, aging, breakdowns, births if it lasts long enough, and all the other things real populations require. Population scale is not a side question. It is the difference between an outpost and a civilization. Then there is the ecological side, and this may be one of the most underestimated problems in the entire discussion. Earth's biosphere is not a simple machine we fully understand how to duplicate. Closed ecological systems are difficult even in controlled experiments on Earth. Nutrient cycles drift, microbial communities change, pests appear, contaminants build up, plant growth can become unstable. Recovery from ecological disruption is difficult even when the surrounding planet is still there to absorb mistakes. In a sealed habitat, those same problems become more dangerous because the habitat itself is the only environment the people have. That means ecological instability is not just a maintenance problem, it becomes a survival problem. If the food system is disrupted, if the air handling ecosystem drifts, if contamination spreads through a closed loop, the colony does not get to lean on Earth like natural recovery. It has to solve the problem internally, with limited volume, limited biodiversity, and limited margin for error. So the idea of building a closed human habitat is not only about engineering walls and power systems, it is also about trying to stabilize a tiny artificial biosphere, and that is much harder than public discussion usually admits. A common response is that future settlements will simply have plenty of energy, but energy is not the same thing as simplicity. More energy helps, but it does not erase the rest of the problem. You still need raw materials, spare parts, labour, expertise, habitat integrity, medical systems, recycling efficiency, mental health support, governance, and long-term maintenance. Energy can run machines, grow lights, pumps, thermal systems, and industrial processes, but it does not automatically create a self-sustaining civilization. It only powers the effort to keep one from failing. That distinction matters because people often use energy as a universal answer. Build more reactors, build more solar arrays, generate more power, and the settlement works. But a functioning society is not just a power budget, it is an interlocked system of ecology, industry, health, logistics, repair, and social order. A colony can have plenty of energy and still fail if it cannot maintain its life support loops, produce enough food, handle medical crises, or replace critical hardware. Energy helps everything, but it does not solve everything. This leads to the hardest sentence in the whole subject. If a colony cannot survive without regular shipments from Earth, then it is not a backup civilization. It is just an outpost that depends on the original planet continuing to function. That means it is not really species insurance. It is an extension of Earth's infrastructure, placed somewhere harder. A true backup would have to survive crop failure, medical emergencies, machinery loss, instability, generational turnover, and ecological disruption without Earth stepping in to save it. That is an extraordinary standard, and no off-world settlement is anywhere close to meeting it. This is where a lot of the marketing around space colonization becomes misleading. It talks as if the mere existence of people on another world means humanity has become resilient. But resilience is not measured by whether a flag is planted or whether a habitat exists. It is measured by independence under stress. If the settlement fails the moment shipments stop, then it has not escaped Earth's vulnerability. It has only extended it into a harsher environment with worse margins. That does not mean human activity in space has no future. It can grow. Industry in orbit can grow, scientific stations can expand, mining, manufacturing, communications infrastructure, and robotics may all push farther outward. Those are real possibilities. But that is different from saying humans will casually transplant Earth-style civilization into the solar system. The environment is harsher, the logistics are more punishing, and the biological dependence on Earth-like conditions is much deeper than optimistic language usually suggests. So the more realistic conclusion is not that space development is meaningless, it is that it may happen in a very different form from the one people advertise. There may be more machines than settlers, more industrial systems than cities, more remote operations than self-sustaining colonies. Human presence may exist, but as a thin layer on top of a much larger technological support structure that remains difficult, expensive, and fragile. And that points directly to the next problem. Because once you look at what actually works in space, one comparison becomes uncomfortable very fast. In many cases, the best tool for exploration is not a human at all. It is a machine. Robots do not need pressure, water, sleep, emotional support, or radiation-safe biology, and that changes the entire logic of why we would send people in the first place. Human presence sounds like the highest form of exploration, but that is not the same as being the best tool for the job. That is the uncomfortable comparison at the centre of modern spaceflight. Yes, humans can improvise, react, notice unexpected things, and inspire other humans in a way machines do not. All of that is real. But if the question is not what feels most meaningful, and instead what works best in space under real physical constraints, robots often win very quickly. They do not need oxygen, water, food, pressure, temperature, comfort, sleep, mental health support, or protection from the same kinds of radiation damage. They are not carrying an entire biological support system just to stay operational. That one difference changes almost everything. A robot mission starts with the scientific or industrial objective. A human mission starts with survival, and only then can it add the objective. That means the mass, volume, and complexity of a crewed mission are already much larger before the actual exploration even begins. If you send a robot, most of the payload can be dedicated to instruments, mobility, power, communication, and mission hardware. If you send a person, a huge fraction of the mission gets consumed by keeping the person alive, functioning, and safe enough to come back. That is why robotic payloads are so much easier to launch and protect. A probe can be smaller, lighter, and cheaper. It can tolerate colder temperatures, harder radiation, longer travel time, and long dormant cruise phases more easily than a crewed vehicle. It does not complain, panic, get dehydrated, suffer bone loss, or require medical care. It can accept one-way missions. It can be sent into environments that would be unacceptable for humans. It can even be treated as expendable if the mission goal justifies the risk. None of that is true for a crewed mission. The difference becomes even clearer when you look at actual history. The farthest and most scientifically productive exploration in the solar system has mostly come from robotic missions. Orbiters, landers, rovers, flyby probes, and space telescopes have transformed what we know about planets, moons, comets, asteroids, and interstellar space. Humans have done remarkable work in low Earth orbit and on the moon, but the greatest physical reach of our civilization has been robotic. That is not an accident. It is the direct result of machines being much easier to send through hostile environments over very long distances. And the irony gets sharper as robotics improves. The better our autonomous systems, sensors, mobility platforms, and remote operations become, the weaker the practical case for sending people into many of those same environments. If a machine can survive longer, travel farther, cost less, and still return high-value science, then the burden shifts to human missions to explain why the much higher biological and engineering cost is justified. Inspiration is real, but it has to compete against a very strong operational argument. This is where telepresence becomes especially important. If communication delay is low enough, robots controlled from orbit, from nearby stations, or from relatively safer locations can capture much of the flexibility people associate with human exploration. A human crew might remain near a target instead of landing directly on it, and operate robots on the surface with much lower risk. Even where real-time control is not possible, growing autonomy means machines can perform increasingly complex tasks with less direct supervision. So the frontier may be explored on behalf of humans without requiring human bodies to absorb the full danger. That point matters because it changes the whole logic of future exploration. It suggests that human involvement does not disappear, but it shifts. Humans may design the missions, supervise them, interpret the data, operate robotic systems from safer distances, and build the industrial networks that support them. But that is different from saying humans themselves will physically dominate the deep frontier. The better our machines become, the less necessary it is to place fragile biology at the point of maximum danger. There is of course an emotional objection to all this, and it is a serious one. Many people feel that robotic exploration is not enough. They want human beings to stand on alien ground, look over alien horizons, and physically extend civilization outward. That desire is understandable. It has cultural, symbolic, and emotional power. But it is not an engineering rebuttal. It does not remove the mass penalty, the radiation problem, the life support burden, the medical risk, or the mission time. It only explains why people still want the mission despite those facts. And that is where the standard becomes very hard. The universe does not reward what feels bold, it does not care how inspiring the mission patch looks. It only responds to survivability, energy, mass, time, and reliability. If machines can do the work better, cheaper, farther, and more safely, then human travel has to justify itself against that baseline. In many cases, especially beyond a narrow sphere around Earth, that becomes difficult. So this may be the final blow to the classic dream. Perhaps humans do not become the dominant physical explorers of deep space because we are too biologically fragile, too heavy in system terms, too short-lived and too expensive to support compared with machines. Perhaps the things that truly spread through the solar system and beyond are probes, teleoperated systems, autonomous platforms, and robotic industrial networks carrying human knowledge farther than human bodies can go. If that is true, then the real spacefaring descendants of human civilization may not look like people in helmets crossing the stars. They may look like machines built by earthbound intelligence and sent where flesh cannot reasonably survive. And that leads to the final conclusion, because once robots start outperforming humans across distance, survival, cost, and endurance, the question is no longer whether space travel is possible in general. It is whether human space travel beyond a narrow region near Earth is actually central to the future at all, or whether it was always going to be a marginal exception inside a much larger machine-driven expansion. The wrong question is whether humans can go to space, because that question was answered a long time ago. Yes, humans can go to space, briefly, carefully, and at enormous cost, inside machines that work constantly to stop the environment from killing them. That part is real. The harder question is whether humans can travel through space at meaningful scale, meaningful distance, and meaningful frequency, without the whole effort collapsing under biology, physics, time, and logistics. And once you ask that version of the question, the answer gets much darker. Part of why the dream survives is that every single barrier taken by itself looks at least partly manageable. Vacuum is deadly, but you can build pressure systems. Radiation is dangerous, but you can shield some of it. Microgravity harms the body, but you can exercise, maybe add artificial gravity later. Distances are huge, but you can plan transfer windows and optimize trajectories. Rockets are limited, but you can improve propulsion. Psychology is fragile, but you can train crews. Medicine is limited, but you can prepare, screen, and carry equipment. That is why optimism keeps coming back. Every problem, when examined alone, seems solvable enough to keep the story alive. But that is also exactly where the real problem hides. These barriers do not arrive one at a time. They stack on top of each other, and each one makes the others worse. More shielding means more mass. More mass makes propulsion harder. Harder propulsion often means slower trips. Slower trips mean more radiation exposure. Longer trips also increase medical risk, psychological strain, maintenance burden, and system wear. Larger habitats may help with crew survival, but they need more structure, more power, and more propellant. Artificial gravity might help, but only by making the spacecraft larger and more complex. Landing systems add mass. Return systems add even more. Human space travel may not fail because it hits one single impossible wall. It may fail because too many punishing walls arrive together and keep reinforcing each other. That is the central conclusion. The universe may be open to intelligence, but it may not be open to human bodies in any broad or comfortable sense. Intelligence can cross distance in many forms. It can move through signals, telescopes, robotics, automation, software, and perhaps one day machine systems far beyond what we currently have. But the human body is not a general-purpose space organism. It is a very specific product of Earth. It was shaped for 1G, for a thick atmosphere, for liquid water, for stable pressure, for modest radiation, and for a planetary biosphere that does most of the life support work automatically. There is no rule saying the larger universe has to accommodate that design beyond the one world that produced it. That sounds pessimistic, but it may actually be the more mature view. Humanity may remain mostly local and still become genuinely cosmic. We may expand into nearby orbital infrastructure, perhaps into limited planetary outposts, maybe into cislunar industry or tightly supported settlements. But our main reach into the wider universe may come through instruments, observatories, robotic explorers, automated factories, and data. In that model, we do not physically spread through the stars the way science fiction often describes. We study them, map them, measure them, reach them through machines, and send outward the things we can build more easily than we can survive. That is not failure. It is just a different kind of success. It means accepting that knowledge can go farther than flesh. It means understanding that presence is not the only way to matter. A species can remain largely tied to its home world and still build a civilization that sees deeply into the universe, affects it technologically, and leaves artifacts far beyond the range of the body. So when you hear that humanity is destined for the stars, it helps to slow down and ask what that sentence is really demanding. It is asking whether a short-lived, radiation-sensitive, pressure-dependent, water-filled organism can transport a miniature version of Earth across distances so large that even planets are separated by mission-threatening timescales. It is asking whether your bones, your blood, your eyes, your lungs, your psychology, your food, your machines, and your fuel can all remain intact long enough to cross an environment that was never built for you. It is asking whether every weakness of the human body can be carried, protected, repaired, and sustained inside hardware without the cost and complexity overwhelming the mission. And the most unsettling answer may be this: space travel is not impossible. Machines can do it. Probes can do it. Signals can do it. Human beings can even do a little of it close to Earth, for short durations under extreme support. But human space travel beyond a narrow bubble around Earth may never become normal, broad, or civilizationally central. It may remain rare, fragile, and marginal, not because human ambition is too small, but because the universe is too large, the body is too dependent, and the engineering penalty for keeping a person alive is too severe. That may be the final correction. The future may still belong to space, but not in the way people usually mean. The cosmos may be reachable by intelligence while remaining mostly closed to the human body itself. And if that is true, then the real story of our species is not that we will physically conquer the stars, is that we will learn how far our minds can go, even when our bodies cannot. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.